Welcome to part 2 of our podcast on keeping AI and autonomy safe.
So, Damien, you talked earlier about prototyping. So, how do you go from prototype to mass market fleet distribution?
That's an interesting challenge, interesting question, which I wish I had the actual answer to, because I think the person who figures out the complete answer to that i- you know, is going to be a genius. Uh, I think at this point it's about understanding exactly what those problems are to go um, from prototyping to mass kind of fleet distribution, and where there are benefits between the two. It's not all negative. So the first thing, and I think I touched on this earlier, you need a software defined vehicle. You need a software defined platform as a starting point. So, step one is you got to think about the car not as a set of brakes or an engine uh, or even a video entertainment system and radio and a disparate collection of different technologies. It has to be um, a single entity on which you can put your autonomous systems, and it has full control over everything. It can balance workloads. It can bring to bear um, uh, uh, different types of processing as required. If you think about it, if it, and this is a reflection on how we drive as individuals. When you're driving in a city, there's a lot of things you have to be paying attention to. So the information on the city there's an information overload, and you've got to be able to filter stuff out and focus on what's really important as a driver. Very different to traveling at high speeds on a highway. It's um, a different challenge, and therefore you have to be able to change the car to recognize different workloads in those different sets of situations. And we're currently not thinking like that in the way cars are being defined or vehicles are being um, uh, defined. Um, I think there's some interesting challenges about processing density. You know, the, thinking about the idea of junk in the trunk, which is how most of the prototypes are. You drive around with essentially a data center in the back of the vehicle. Um, you have to take all of that into very high density processing capabilities that are cost effective. So there's a cost element and a footprint kind of challenge that has to be addressed. Um, Statistically, you suffer as you go from small numbers of vehicles to large fleets of vehicles. You suffer from clustering, and what that really means is if you have a one mistake in your AI system, when you get to large numbers, it gets punished more because you expose the that edge case much more frequently. And if you fail on the edge case, you will repeatedly fail on that edge case. So um, this concept of um, the statistics going against you as you go to fleet because of clustering against edge cases is something that's not well studied or well understood at present, um, and needs to be. There needs to be work on extrapolating what we've learned in a small number of vehicles to identify the problems when you get that large fleet of vehicles. Um, so as I say, I promised not to tell you how to get from prototyping to mass market fleet, um, but there are some definite things that you have to solve. And for us, as our area of kind of interest and expertise is that platform kind of aspect of it. The If you're going to invest billions of dollars, because it will take billions of dollars of investment in building autonomous applications, you need to know that you can separate that investment from an underlying kind of implementation methodology. You can't spend billions of dollars on one set of technology for one car system and discover that your car system has to change or the technology needs to change and be refreshed. You have to be able to take that investment and have it last years. It's also another aspect of that is if you think about how long the service life of a car is, typically, or a vehicle, even more so in trucking, you're looking at a 10 to 15 year kind of life cycle. Well, can you imagine the kinds of technology that you would want to be putting into your AI system 15 years from now or 10 years from now? We have to design platforms in cars to be extensible in a way that just isn't at all in the way that they're kind of built right now. And a great example of this is if you get into a car with a entertainment system that's 2 or 3 years old, or even worse, if you go and look at one from 5 to 7 to 10 years ago, you look at it and you see immediately the disconnect between the car technology or that in-car screen and what you're used to seeing in your hand on your mobile phone, for example. Um, we've got to design a platform that's capable of lasting, being expanded and being serviceable as an autonomous system, 10, 15-year kind of field time.
I think you hit the nail on the head there about software defined. I think that's the way the industry is heading, and almost the underlying hardware is somewhat a commodity or a don't care. Because I think the other point you made is that the applications or the different environments that the vehicle is going to be in are going to vary dramatically. As to take your example of driving down the high street where there's pedestrians and signs and there's a whole load of stuff going on versus cruising down an empty highway at 70 in the middle of the night, right? It's very different use cases. So those workloads are going to be very dynamic in nature, and the underlying hardware then has to deal with that dynamic nature as well as the software as well. So I think having an approach that enables you to abstract away from that hardware and almost you don't care what's there, as long as you know you've got enough compute performance overall, you need to be able to dynamically allocate. I think that becomes really, really compelling.
That sort of leads me to two kind of use cases that are kind of interesting. One was a conversation I had with a large truck manufacturer who saw the business model for trucking being one of the best kind of examples of near-term opportunity for autonomous vehicles. And they were looking at, do we as a trucking company actually become a company that rents trucks by the time slice or by the route, and our vehicles have no drivers, and they simply run almost like trains on roads. They run between depots. We design our depots to be next to highways so that our AI challenge is the challenge of the highway, which is a simpler one than driving around New York or driving around cities. And what we do is we have people drop off loads at these depots, and those depots are connected to autonomous vehicles that move them to other depots to be collected. And we just have a fleet that is constantly moving between these kind of hubs. All the advantages that you can bring to bear, 24-hour a day service, no 8-hour limit on the driver, the fact that you can put these things into convoys. If you've got 4 or 5 of them going to the same place, they can drive, with a few feet between them, all linked up, and there's huge kind of benefits. So that was one that was very interesting. The other one that I thought was an interesting kind of view of of the application of autonomy is Deutsche Bahn in Germany. And Deutsche Bahn have a number of challenges and opportunities that they see autonomous vehicles helping with. So one of the challenges is they have to keep open railway stations all over the place, even though some of these railway stations make no economic sense because they have a public service requirement to meet. So they keep rural, remote, non-profitable, non-cost justified stations open. The other aspect that they recognize as something that they have is they actually understand the travel patterns of people around Germany better than anybody else. They know where people are going day in, day out. They know door to door kind of travel. And so they're looking at how do we add to our infrastructure where we've got high speed hub to hub connections through the train with last mile personal delivery services. So the equivalent of the taxi. Now in a city, that problem is well solved. You know, if you get off a train in any German city, there are 100 cabs waiting to take you wherever you need to go. If you get off a train in a rural station in the middle of nowhere, there isn't anybody waiting to take you anyplace. And so autonomous vehicles in those situations all of a sudden make sense in solving the last mile problem. So it's very interesting, I think, to the question that Mary Beth asked, which is, you know, how do we get to prototype to mass market fleet distribution? I think focusing on some of these low-hanging fruit use cases where we can narrow the definition. We're not trying to build a vehicle that can do everything. We're trying to build a vehicle to do very specific contained set of tasks, maybe the kind of the next or the real first manifestation of autonomous vehicles.
The thing I like about those examples are those are the market drivers, right? Those are the things that have a clear path to market growth and return on investment. You know, it's the dirty and difficult tasks that have a cost, and by having the autonomous system, you know, creates that return on that investment. I think that's why we see things like, well, if you look at our work that Core AVI has been doing with NASA, for example, they're trying to do Mach 3, low boom Mach 3, Mach 2, Mach 3 flights, and they're trying to do it using autonomous systems and with a windowless cockpit to be able to achieve certain form factor to achieve those Mach speeds. You know, using GPUs and using the products from Core AVI, we've been able to allow them to support sensors, support sensor fusion, and video to allow them to deploy these windowless cockpit systems for flight. It's a great example because in order to achieve the objective, they needed to deploy, you know, safety certifiable GPUs with our solutions. Another good example would be, you know, Airbus, right, where programs were involved with Airbus for autonomous boom refueling in air, where clearly, you know, human error is the biggest issue that occurs with trying to do fuel refuel boom refueling in air. And so by deploying graphics processors and some of the compute algorithms that we've supported Airbus with, they're able to deploy this in an autonomous fashion. So those are different corner cases, but those are clear examples of areas where, you know, there is a real return on investment by deploying these technologies.
So we can do it at Mark 3, so we should be able to do it in autonomous vehicles okay then, right?
Neil, we've both seen you drive, and we know that being able to do it at Mach 3 maybe just about enough to keep up with you.
So what's Core AVI's role in all of this? What's our contribution?
Well, I think it's important for the industry to have a good, strong set of open standards on which to base this this development and application creation going forward. I think one of the things that we're seeing from a lot of organizations across many industries is the challenge. If you don't set out with a platform that has a really strong safety credential, bolting safety capability on at the end is impossible almost. Not almost, it is impossible. It's very, very difficult to bolt safety on. So you need an approach that you know is going to deliver or be deliverable on a platform of technologies that are robust, have all the safety kind of certification capabilities that you need for your application. Really the way to achieve that is open standards. It's not product based. It's even lower than the product. It's standardization. And we're not the first industry to recognize the benefits of that. If you think about how abstracted the internet has become, because it started off with very simple sets of open standards on which it built more open standards, and therefore by the time you get to build applications, you can do amazing things because you're not building all of the foundation. So our contribution really is to the foundations of the technology that you need to do this. I think our biggest single contribution to date has been Vulkan SC. That's something that we recognized was a very powerful standard in terms of Vulkan for abstracting away from the GPU and other emerging technologies. There's no reason why Vulkan can't be used for NPUs and specialized hardware. And so the Vulkan SC standard does a number of important things. One, it is a high performance abstraction from hardware, so you're not paying a huge penalty to implement it. Two, it is a safety engineered standard right from the ground up. And thirdly, it has got a wide industry, a multiple industry adoption. So we've seen everybody from tech companies in terms of silicon vendors, software vendors, but also end user markets and industries contributing to the creation of the Vulkan SC standard. So as being the company that started that process and has galvanized support around it is something we're very proud of, and we actually think is going to be an important step in the pathways to safety for many applications, not just autonomous applications.
And it's flying, Damien, right? I mean, it's flying. NASA's
Yep.
using it today. It's in flight.
Yeah, I was going to say it is something that's coming from a proven pedigree and a proven background. It's not a field of dreams situation. This is something that's very, very real. So that's our big contribution, but that's not our only contribution. We've been looking at, what are the challenges of taking your neural net and delivering your neural net in a safety confined environment. And there are a lot of challenges to that. If you think about the way neural nets operate, they are very memory intensive, and memory management is a challenge in safety critical applications. I don't want to get too under the hood in terms of the technology, but the idea of building a safe system is that it is constrained. And by constrained, it means you understand how it is going to operate. The important thing about safety environments is they have to be deterministic, and by that we have to know that things are going to work in a certain time. You can't be waiting for an AI decision to be made whilst a car has been driven or a plane has been flown at Mach 2 or Mach 3. You need to know things are going to happen when you expect them to happen. They need to be bounded. You can't run out of memory. You can't have a process run that all of a sudden needs an extra 4 gigs of memory to execute on, and you're expecting the car driver to, add some more memory in order to decide whether they're going to turn a corner. Those things can't happen. So there's a constraint element. So on top of the Vulkan SC, now we're looking at, this is a great tool, great platform. How do we solve some of these additional technical challenges about the implementation of complex AI applications or compute applications or vision processing applications inside constrained resources? Um, yeah, taking that challenge of the trunk full of equipment has got to get down into small packages or systems that you can deploy in the car. And so there's a lot of work going on at Core ABI in this field.
Okay, so we have Vulkan as a functional building block. What would be the alternative to Vulkan?
I think there's a number of toolchain options that are out there. CUDA is probably the biggest of those and the most established, and clearly one that we've seen a lot of people start out with in terms of trying to solve some of these problems. Um, you quickly hit the issue of finding a pathway to safety from CUDA, and um, that's a challenge with any proprietary technology. One of the things that's uh, you see when it comes to standards in terms of um, certainly safety standards, being a single vendor trying to get um, a safety standard ratified is very, very difficult. There's a realization um, that you want to bring multiple parties to the table to create standards. That's really the entire principle. Um, and then the other approach is, and we've seen people do this, which is the heavy engineering approach, which is that you try and define and build an entire proprietary system yourself, and you build up selecting tools and selecting hardware and engineering bottom up. And to be fair, that was the way that the avionics market was 10 to 15 years ago. It was, we'll build our own piece of hardware to do X, we'll build our own piece of hardware to do Y, because the ecosystem and the tools and the platform capability wasn't there. And we've seen this steady realization in avionics that the real value lies in building your applications, not in building the platform to run your application on. And again, you can see an analogy um, in the internet, in applications, in business applications. It's no longer about the hardware on which you run it. There's a myriad of different hardware solutions. It's about what's the functionality of the application that you're building, and that's where the real value lies. And you have specialist companies who build platforms, and I think that's the way um, uh, we see this going, because it has to. It's just so the alternatives right now are build your own platform from scratch, or there are a few tooled alternatives, CUDA being one of them. The problem there is perhaps a lack of pedigree in terms of path to safety.
Well, and a lack of scalability as well, because you're kind of in jail at that point as well, right? So you're beholden to using that underlying hardware for forever until you want to make the change, and the longer you leave it, the more expensive it gets to switch.
I think flexibility would be another, right? With Vulkan, you get a single API for graphics and compute designed for parallelism. I think with CUDA, you have some challenges where you need separate graphics APIs, when deploying those types of applications with CUDA, and it's not designed for parallelism. Yeah, I think you mentioned Vulkan as a foundational building block, and determinism is the foundation of safe system design. I will say, looking at who's contributing to these open standards in Kronos, the Kronos group that, defines these standards, you have members from automotive, you have members from avionics, and you have members from industrial, all contributing to these standards. So it's quite a powerful consortium that is involved in defining and solving, this platform problem.
And you mentioned another really important word there, Damien, pedigree. When it comes to safety, pedigree is really important, right? We all know, for those of us who've been in it for a long time, there's work to be done to make systems safe. For those who are just getting into it, they're beginning to realise what it takes, and that pedigree counts for a lot. And that's something that we've got in spades. We've been doing this for a long, long time. We've got lots of experience under our belt. So, that's a huge benefit for a lot of the customers we're engaging with, both, historic customers and new customers as well. It's that risk mitigation. I think the other interesting point you made as well is around the safety. I just wanted to reiterate that we are seeing customers and potential customers actually kicking the can down the road from a safety point of view, which is, I guess it's inevitable, because as we said earlier on in the conversation, there's such a huge investment going into training models and that whole AI training and understanding, and maybe little to no investment and investigation to the safety deployment of that. And whilst safety truly is a cradle to grave domain, it's okay to come in part way through. And I think, to touch on your points around Vulkan SC and some of the other activities we have around OpenVX, for example, it's fine, because we have a path there as well. We can take model outputs from the popular tools like Caffe, TensorFlow, PyTorch, and we can make them deterministic, and we can go and deploy those as well. So we've got a path to deployable safety, even if you're partway through your development and your investigation phase. So I think there's goodness there as well.
I think a good example of what you're describing is really urban air mobility. We've seen a number of customers and partners that began their proof of concepts on, using NVIDIA CUDA and other, call it, proprietary tools. And when it's time to go to mass deployment or bring the product to a point that it can enter into flight, they obviously need real safety. And what they've described to us is, they're essentially dead in the water, and they have to do redesign work, and there's challenges because they don't have a path to bring that prototype to safety certification and to take to flight. And really, that's where these open standards solve that problem, right? By not using, for example, CUDA, and by using Vulkan and OpenVX, you have a direct path from prototype to production. And that's something we're seeing a lot of our urban air mobility customers begin to accept and take that type of approach.
And whichever market you play in, right, scalability's got to be important for you, because it's TCO, it's engineering dollars. So if I can be assured that I can develop on one piece of hardware today, but tomorrow if I decide I want to change hardware architecture, and that's not going to impose a huge tax on me from a software point of view, that's got to be a benefit. And I think that's what Vulkan brings me, if I think of it from a customer perspective. And we all know, right, the architectures leapfrog each other from generation to generation. Today one architecture might have the advantage, but tomorrow it may be a different architecture. If I can abstract away from that and know that I can make that hardware switch and still maintain the vast majority of my software stack, then that's a huge benefit to me in engineering costs, but also time to market, time to certification as well. It's better for everybody.
To pull up another, golden oldie, if you think about the Amstrad personal computer, when it first came out, the PWC, which was basically a printer and computer to link together to create desktop publishing. The application in that piece of technology was actually written for the chipset and the technology and every everything was tightly coupled. You change the printer technology, you have to rewrite your application. And I feel a little bit in the autonomous market space, we've seen a lot of people sort of getting into that sphere of kind of tight coupling between the autonomous solutions that they're trying to build and the way that they are trying to build them. And it's really important to decouple. You wouldn't buy a PC today if if it meant that you had to go and get a version of Word specially compiled and and changed to run on your hardware. We are we're so used to the concept of abstraction in the business and personal technology world. I think we're now looking for the same in the industrial application worlds, purely for this reuse. Um, it, time to market has to be, a real goal for the long-term viability of a lot of these projects, and you cannot do time to market if your engineering stack is too big. You need to be abstracting away different layers um, of your application stack or your solution stack, so that you're not reinventing the whole wheel every time.
Did that answer your question, Mary Beth?
I was going to say, so I think, Mary Beth, in summary, what's our contribution? I think it's clear we're delivering a pathway to safety by applying our expertise around solving these problems we're describing under high performance demand and high constraint, and where true safety is required.
I think we're front and center in that.
Yeah, exactly. We're your expertise on your path to safety, I think sums it up. Thanks so much, everyone, and I'm sure we're going to be hearing a lot more about the important role of keeping AI and autonomy safe. I'd like to thank our guests today, and we look forward to bringing you more information in the next podcast episode in our series, and we look forward to connecting with you all again soon. Thanks for listening today.